Hi everyone. This lecture is on Hopfield neural network architecture. This is primarily used for image applications in terms of image recognition. Is one of the application. This network is a lot more easy to understand compared to other networks. It's essentially a single layer network. It's fully connected with no self feedback. It is a feedback network. It uses in terms of the neural dynamics, it uses the standard the weighted summation functions, and also it has what's called sigmoid transfer function. It uses what's called the Hebbian training. We'll look into that. So basically what I'm going to look in would be to work out some hooked out example. That's the easiest way to understand any network. Then first of all we'll see how to do this in training mode. Then we'll see how it can be done. It can function in recall mode. We'll also find out that in terms of image recognition, if an image recognition system is implemented with Hopfield, you would find that this neural network recognition system would have a lot more tolerance for image variation compared to conventional algorithms. As you can see here, you can see here Hopfield is essentially a single layer network. All the input, primary input, which are usually in binary format, they're correspondingly connected. And this input layer, the function of this input layer is to convert any kind of inputs into bipolar binary. And the output Hopfield layer, it's a fully connected network. It's a fully connected feedback network with no self-feedback. Hopfield is essentially a single layer, fully connected feedback network with no self-feedback. I'll show you in a minute. Input layer is there just to convert unipolar signals into bipolar binary using sigmoid transfer function. It can also be used. It is primarily used for image recognition. As I indicated here, Hopfield essentially a single layer network. The input layers are there just to convert unipolar into bipolar signals. Without that, training algorithm would not work. When you look for image recognition systems, the images are assuming they are black and white. Images are represented by bitmaps. Corresponding to, for example, this is a representation 5 by 7 matrix, which essentially creates various types of characters. So if you want to represent this image, whichever is 1 in memory, that will be represented by a 1, and whichever pixel is off, that is represented by 0. That is the pixel on binary 1 and pixel off binary 0. So when it is stored in memory as a bitmap in this format, that is representing ones and zeros. So essentially, if you linearize it, image bit linearize and make it as a single input vector, that vector becomes that's 5 ones, like a next row, there's a next row, next row, next row. So it essentially becomes a 35-bit input vector, and that represents an image. So in Hopfield network, basically you feed this image vector with the number of input pixel as an input vector, or as an input. So the image input vector to the Hopfield network. So this Hopfield, to be able to recognize the images based on 5x7 bitmap, you need a 35 element Hopfield network. In general, corresponding to this, as indicated here, let's look at the generalized Hopfield network. This is a 5-element Hopfield network. You would see that each of the primary inputs, x inputs, that's x1, x2, x3, x4, x5. These are connected correspondingly elements. So that is, one is connected to one, two is connected to one. So the function of this neuron is essentially what it does. It has got only the transfer function, which is signal transfer function. It essentially converts into whatever type of signal that you have. It converts into bipolar signals. That's thing. And the other inputs here, as you could see, they are fully connected feedback networks. That means what it means is, so for example, one is connected. If you take this one, it is connected to connected to 5, connected to 2, 3, 4, and 5. This is not connected to 1. Similarly, if we take say a 4, that's 5. For example, 5 is connected to 4, 3, 2, 1. Wherever there is a dot, means there is a connection. If there is no dot, there is no connection. For example, 5 is connected to 1, 2, 3, 4, but not to itself. That's called, there is no self-feedback here. Similarly, if you take number 2, that's the number 2 is the middle line. You see it is connected here, here, but not to itself, which is so it is this connection is like representing the network in what is called matrix format. So that's generalized network architecture. Now what we will do is we'll look into an example how to obtain the network. The best way to do that is we'll go through an example how it is how a network is created, and how it is trained, and how it is going to be used in recall. One thing that we had to know, all these operations from Hopfield network involves most of them are matrix operations. Some basic introduction to basic review of the matrix operations will be very helpful to understand how the network Hopfield network training is done. So we're going to look into some quick overview of matrix operations. Look into this basic matrix multiplication. Again, whenever you have two matrices, M1 and M2, with number of rows and number of columns, and say matrix 1 has got R1 number of rows and C1 number of columns, and whereas the matrix 2 has got a row 2 number of rows and then C2 number of columns. To be able to multiply these two matrices, the columns of the first matrix have to be equal to the rows of the second matrix. So the resulting matrix that you are going to get would be, if we have the first matrix R1 row R1 columns and C1 columns, and the matrix 2 has got row 2 columns and C2 number of R2 number of rows and C2 number of columns. To be able to do this, the C1 has to be equal to R2. So the resulting output matrix is would have R1 number of rows and C2 number of columns. That is what is called the inner dimensions must be equal. That is, the C1 must be equal to R2, or R2 must be equal to C1. Examples of that is, for example, if we have 2 by 3 multiplied by 3 by 4 matrix, these three are equal, so the resulting matrix would be a 2 by 4 matrix. Another example is if it is a 4 by 1 and 1 by 4, what you are going to get would be 4 by 4 matrix. If you look at this the matrices, example, this is a 2 by 3 and 3 by 2 matrix. So when you have a 2 by 3 matrix, what you're going to get is 2 by 2. So if you, in this case, you take the first row and multiply it with the first column, what you're going to get would be the first element. Okay, and when you take the again first row into second column, then you're going to get the second row. That's first row and first column, that gives you 58, and the second row into and the first row into second column will give you the second element. And then here when you multiply this row into that column, you get this element, and if this row into that column will give you the fourth element. So a resulting matrix is going to be 2 by 3, 3 by 2 will be a 2 by 2 matrix. Again, in case of the Hopfield network, in a Hopfield network, you essentially start with what is called 0 weights, and from when you want to train the network, the weight matrix would be amount of weight change that you want to make to the original Hopfield network would be, you take input vector x. If input vector x is the linearized image representation, then if you multiply the transpose of the x multiplied with x minus the unity vector, then that would give you the weight change that you need to make to the original network. Let us say you have a binary input of something like, say, x equal to 1 1 1 minus 1. The transpose of obviously a row vector is going to be a column vector 1 1 1 minus 1. So if you multiply x transpose times x, you remember first row into all the first column would give you that element, that is the and then first row into second column will give you that element. So if you multiply all these, that gives you the first row. If you multiply with that one, this will give the second row. If you multiply with that one, it will give you third row. If you multiply with the last one, it will give you minus 1, 1 minus 1 minus 1 and plus 1, that is the last row. That is the 4 by 1 times the 1 by 4 will give you 4 by 4 matrix. So so if you can understand this one, again this is a and there is 4 by 1 times 1 by 4, and this one is a 1 by 5 times 5 by 5. Then in that case, what you're going to get 1 by 5 matrix. This part is used in the training mode, and this part is used in the recall mode. In a recall mode, usually have a test input, which is an input vector, and then you have a train network. Whatever you say for a 5 input 5 element network, you have 5 by 5 matrix. So if you apply the 5 input vector, when you multiply first row, that you have only one row times one column will give the first element, one row times the second column will give the second element, and again multiplied with third will give third element, multiplied with fourth column will give you the fourth element, and when you multiply with this one with the last column would give the last element. So based on this we can do the recall mode. So during the training you would use this operation. During the recall you would use this operation. Okay, with that some basic background, we can go into training of the Hopfield network. Now I want you to go to the there's a document on Hopfield. It's a PDF file on Hopfield network. So if you look into this, we'll find it has, this one has some numeric examples how to do the training. Okay, let's look into the training example. Hopfield uses what's called the Hebbian training algorithm. What it means is if the inputs are identical, then the that should be if the input is same as output, if both of them are negative, then it is desirable. That means we should increase the value of the weights. On the other hand, if the inputs and desired values are different, whether d equal to -1 and his computed value is +1, or desired value is 1, or and then computed value is -1, in both cases that's not desirable, therefore you want to decrease the value. So if the inputs are going in the right direction, then you want to encourage it, that is by incrementing the values. If on the other hand, if the inputs and the desired value going in different directions, we want to make sure you want to discourage it by decreasing the value of the changes. That's by decrementing the values, which will be the same thing as, for example, when the amount of weight change, you do it by alpha times say y times dn. Y is the computed value, d is the desired value. Obviously, if both of them are 1 or both of them are negative, that is going to be plus. If either of them, one is plus and one is negative, then obviously they're going to be decremented. Now let's look into one network training and recall with an example. Let us say that this is page number page 161. Sorry, it's on page 162. Let's say that this is an example that illustrates how to do the BP Hopfield network training. We want to train two patterns. They're just 5-bit long. Train Hopfield network in auto-associative mode to recognize the following two input patterns. Auto-associative means actually for image recognition, images input is same thing as output, and that's called, if the input is same thing as output, this is called auto-associative mode, in which case you just need only one input or one output. So you don't need the input and output pairs. You need just one vector. That auto-associate, which is images, just image file is input data, and there is no corresponding output data file. So in this case, we want to train for these two patterns. They are just 5 bits long each. So I want to train. You want to store this image like 1 1 1 -1 -1. And the second image is -1 -1 1 and -1 and -1. Okay, to do the network training, the weight, first of all, you take first element is in a Hopfield network. You start with to be able to store these images. If it is a 5-element network, we need to have 5x5 network. So that Hopfield network starts with 5x5. If we have a 10x10, if you have a 10 input vector, then you need to have a 10x10. And initially you start with 0 values. Now first one, to be able to, the weight change that you need to make corresponding to the first pattern can be given by, for example, x0 is here 1 1 1, you find the transpose of that x0, which is same thing. If it is a row vector, that's going to be column vector. And the weight change is going to be simply multiply the x0 transpose times x minus I. In this case, first the row is x is a row vector. The transpose of x0 is going to be column vector. If you multiply this the 5 by 1 multiplied by 1 by 5, obviously you're going to get 5 by 5 vector. Then you multiply, then you subtract 1 from here. In this case, the I is nothing but a unity 1, all zeros in the rest of the elements. Only the diagonal elements are going to be 1. That's I. So if you multiply this element, the first row, that's first row into all these columns will give the first row. If you multiply this one, you'll get second row. If you multiply the last one, you'll get the last row. So minus 1, for example, is minus 1, minus 1, minus 1, and this is going to be plus 1. So then you subtract the I, which is going to be the unity vector. That is in this case, if you subtract these whitening elements, after that what you're going to get would be delta W0 is this one. So if you add this delta W0 to the original weight matrix, W0 happens to be all zeros. If you add dW0, then you'll get the train network after the first pattern is trained. And this would be the value of the Hopfield network values. Similarly, if you take a second pattern, that is the minus 1, minus 1, 1, minus 1, the corresponding del W1 is nothing, again is nothing but the x1. The transpose of this is this one. So and then subtract unity vector again from this. So if you add the weight matrix, what you're gonna get will be this. That would be the delta dW1. So now add this dW1 to the original W1 previously, and add dW1 gives you W2 vector. So if you add those two, you're going to get this input vector, that is 0, 2, 0, 2, 0, 1. Okay, once you have that one, this has been trained for 2 patterns. So that is the first pattern and second pattern. Now let us see how you get the in the recall mode. Now this is a trained network. So in the recall mode, y is nothing but a transfer function times whatever the input vector, test input vector x, you multiply it by the W2, which is the trained Hopfield network. Then you'll get the corresponding y. Now in this case, I'm applying, obviously whatever that we have trained, when you multiply this, we should get our original vectors. So if you apply first x0, 1, 1, 1, minus 1, minus 1, we have to get the same vector. So if you multiply this and this, for example, the first vector times this, that's the first row and first column would give you the first element. And the first row into the last column would give you, that's a 1, 1, that's 0, 0, and that is going to be, third element is going to be plus 2, and then this is going to be again that's going to be minus 2, and that's going to be 0. So if you multiply these values, what you're going to get will be you got first row into first column gives you 2, again this row into that column gives you again plus 2. If you multiply the last one with this, will give you minus 4. Now we apply what I call the transfer function, that is for value greater than positive values, it is going to be plus 1. For all values less than or equal to 0 are going to be negative values. So obviously minus 4 is becomes minus 1, and then anything greater than 1 is going to become plus 1. This is sigma transfer function, and anything less than 0 is going to be a minus 1. Now you see that this is the same as the original vector, that one. Similarly, you apply your second vector, that's 1 1, the minus 1 minus 1 minus 1, that is the second vector. That is the second vector that we have applied. Let me see. Okay, if you apply the input vector 1, you got that value. The network has, let me see, I did not apply the second one, but if you apply the second one, you are going to get the second vector. The network has got a high tolerance to noise in the input signals. If, for example, if x is 1 1 1 1 1 minus 1 minus 1 minus 1, we change 1 bit. That is equivalent, if you have 5 bits, if we change 1 bit, that's equivalent to 20% variation in the original input. So originally we had 1 1 1 minus 1 minus 1. Now I change to 1 1. First two elements are the same. The last two elements are the same. When the middle element is this is plus 1 and it becomes minus 1. So when you apply this negative 1, you see the original still you get 1 1 1 minus 1 minus 1. What it means, for even if there is a 20% change in the input bit vector, we are still able to get the original vector. Of course, it will be a lot more meaningful if you have a very large input vector, but it would work. Again, you can you have the Hopfield network model, that is the simulation program. You can run it, run through that. In case of Hopfield network, if you are using program. If you are newer one, it's Hopfield input data file. If it's the older version of the program that you have, in this case, input has to be it should be Hopfield dat file. In this case, for the input data file, you specify the number of parameter inputs, training coefficient. In really, training coefficient doesn't have much of a meaning here. You normally set it to 1 because it is actually training is done in one cycle. It's multiplied xt times x will give you the trained pattern for that. So you don't need to have you don't need to go through multiple patterns, nor you need to go through epochs. Each time you training is simply done simply by multiplying xt times x. So that's the corresponding input vector, and then when you go through this, it gives you the corresponding weight changes. For example, if you apply here we are applying 3 patterns like 1 0 0 0 0 1 0 0 1 in the training mode. This is multiple patterns. It doesn't show you all the details of the training. Let me see if I have an example for a single pattern. This one has got multiple patterns. Actually, W0 there is no returns. This is the initially start with 0 bit matrix for the corresponding to the first one, that is delta W0, and then that's a new weight. Then this DW1 is the corresponding to the second pattern. They get new weight because this is corresponding to the third pattern. Weight changes, and you get final weight of this one. Then if you can apply, then this will be stored into a network file, and then with the 5 elements, when you apply any test input, it's going to give you the corresponding output there. Most of the time in a Hopfield network, you should be able to store, theoretically speaking, infinite number of images, but you will find that it has shown that the maximum number of patterns that you can store in an n element network is going to be n by 2 times n natural logarithm n plus ln of natural logarithm of n here. So there is a limited number of patterns you can store. That's more or less it. It's very simple network. Training is very simple, and inputs are simply binary input and binary output. That's more or less about the Hopfield network.